Order of the speakers today, number 2 to 3 o'clock, and this was an 8-minute talk session. Walter, Eugene, Hayden, Mika, Nina, Pavan, Remy. Okay, with this, let's welcome our next speaker.
Wolfgang, the bus starts from the work for the bus starts from here at 4:15.
Correct. So it means so 4:15 here. I make the uncomfortable bell in case you're upstairs. We're gonna walk up. Please double check in your emails the exact location, but it's described to you. You walk up in the front area. There's a small niche. The bus will be stopped in front of the business.
I have the suggestion that you get a flute instead of the bell. So you can follow the flute. Like the rest catch your
But this has some bad annotation because I don't want to lead you astray. But the story from the birth of the flute is not the best one. It's going to lead you to some tasty dinner. Okay, with this, our next speaker, Pierre Bourhis.
Thank you. Everyone hear me? Okay. First, thank you for the invitation. I'm very happy to be here for this great workshop. So today I will present you some work that I've done with these co-authors over the last years about querying sorting over trees, and inspired with all the work that I've done on complex query answering for relational databases, but we apply it for trees. So typically, tree is another structure that you can use for representing your data. And typically, the classical way to query or to express queries over there is not first order logic, but it's in general MSO. And you can express MSO for Boolean queries. And there is another formalism, which is a tree automata. And there is classical translation from one to another. And then you have extension of MSO where you can capture also different nodes of your tree. So you can use first order variables, so you return tuple of nodes, and you also second order free variables, and you return tuple of sets of nodes. So here most of the talk will go to the first kind of queries where you have first order free variables. And typically there are extension of MSO of queries and trees where typically you want to do this kind of counting number of solution, and then there are extension with counting MSO from CRISTAL. And there is query over probabilistic tree representation that we're studying in general of 10 years now. And also questions about enumeration of solution over MSO trees. And there are different papers that worked on that already before. And a big question in particular when at some point when we started this kind of work, it was about maintaining the answers or the structures, this for example, enumeration through updates of the tree. So you not only want to query, but you also want to update the answer of the queries. So typically, the thing is, what we know is, in general, most of these questions are, if you can evaluate them in linear time over the size of my tree, which is really interesting because it goes completely the opposite of things that have been done in relational databases, where typically you don't have one particular language, and in general you have to find restrictive language, and you have to do a dichotomy to find the place where you can do efficient query answering. And so typically what I will try to motivate, and this is kind of long research we've done, is the fact that to answer this question is why MSO query evaluation of our trees is simpler than conjective query complexity evaluation of our relational database. Is there a fundamental ground to explain all these different results in one unified framework? So this is what we have tried to do. So the main thing that we have tried to do is to say that how to represent the solution of an MSO query. So we had a partial answer a long time ago through notion of provenance for trees, and at the time what we showed that this provenance for MSO query over trees can be computed in linear time and by a circuit, and also with a bounded tree width. Typically, what I'm going to talk about after, you will see has a lot of relation also to the work that I've done on the context for relational databases, where you try to have a fine representation of the provenance or of the answer of the query that allow you to do complex evaluation in the context of dense tree was for probabilistic evaluation. So this is the same line of IDs. We have not reinvented anything, but it's just the fact that here you will see it works very well for all MSO. So typically what we do, we use a Boolean circuit to represent a set of answers to a pattern, to a query, where typically you have a singleton where you have variable alpha, for example. And then you say alpha 6 is a variable, and this variable tells you that the variable of my query is mapped to node 6. And you can have tuples of singleton. And typically we want to have a circuit that captures a set of tuples in this way. So typically, the answer of the query are the satisfying assignment of my circuit. And typically what we want to prove is that these circuits fall in restricted circuit classes that allow for efficient complex operation. And so the question is, the task is given a Boolean circuit how to efficiently operate the complex operation that we want over the circuit. So we go to Boolean circuits. So to give you what is a Boolean circuit, so you have output gates that tell you the output, and then you have literal gates like for variables and their negation, and you have AND and OR, and you have some particular also gates sometimes you can use called decision gates. And so you have evaluation, the function that goes from the variable to 0, 1, and typically here we have an example, and you can propagate bottom-up the valuation and to tell you if this valuation is satisfied by my circuit. And then what you have to do is you have to have that the values that you propagate at the output gate have to be 1. Now, this is classical things, and what you can do, you see you propagate in this way, and then you map to 1, so we know that this valuation is accepted by my circuit. So an important notion that we need for the rest of the talk is the notion of assignment. So typically, what we want to do is we want to have a more concise representation of the valuation by looking at only the set of variables mapped to 1. And we'll explain to you why it's important. So typically, in general, we will consider much more assignment than valuation. And so typically, one of our tasks that we want to do is enumerate all satisfied assignment for an input circuit. Is kind of task that we want to do. And I will explain to you later. So for that, we will go to restricted classes that was proposed nearly more than 20 years ago. That's called DDNNF. So DNNF are disjunctive normal form, and the D first is the deterministic. So deterministic means that if I look at two subcircuits, all the valuation of one will be disjoint to the valuation to the same one. So typically, here, this part, if I look at the valuation of this part and valuation of this part, they are disjoint. So for example, here you see that what you can notice is the fact that you have the x have to appear, x have to be mapped 1 here, and here x have to be mapped to 0. Then you're sure in this way that you have, you will not, if you reason here, you're sure that in your reason here, independently, you will not reason on the same assignment of valuation.
So semantic restrictions.
This is a semantic, yeah. And this is in general in Pierre hard to check. But typically, what people have done is so a line of research is called knowledge compilation framework, and a field, typically people try to take any CNF, for example, and try to compile into this kind of circuits. So this is one line of research. Here you will see that we also sometimes, so the work of Dan, for example, show that for some particular conjunctive queries, you have this property automatically. And this is what we try to do. And the decomposability is the fact that when you have a hand, you talk about, you split the variables on the left and the right. And also we need some notions called smooth. It means that if you look at your subcircuit here, you see that you have a variable that y that appear here and a w that appear here, but not in the other circuit. Typically, when it's smooth, you need to talk about all the same variables here and all the same variables. This is important for some of the results later. The same way, smooth is not something automatic. You can check it, but it's not something automatic that you can have. And the last one is zero suppressed semantic. circuit is the fact that you don't talk about valuation, but you talk only about assignment. So typically you don't have negative literals, you have only positive one, and everything that doesn't appear in your circuit just has to be assigned to 0. So what we know about querying circuits. So the first thing is, I will talk about summering just a little, is the fact that if I take a commutative summering and I give a set of assignment of the variable, like a cost function that goes from the variables to the literals of x to k, I want now to generalize it to say what is the value for my circuit. Okay. And what I do the sum of all the assignments satisfied by S, and I assign to all the literals assigned to 1, I give them their value, and to the one that the variable assigned to 0, I give the value assigned to the negative literal. Okay. And what we can prove with a smooth DGNF circuit. If I do that, I can compute it in linear time. Typically, the example I've shown before, when you check the valuation, you take the Boolean summering and you just do the evaluation. It's exactly you can do, and you just generalize it. So typically, we don't need smoothing for a particular kind of function called positive cost function. It means that when the negative literal are associated always to the neutral. That I don't need, if I'm in the case, I just mean one is negative. When I multiply in neutral, it doesn't change anything. So all the information is brought by the value of the positive literals. And in particular, we can do counting valuation and probabilistic evaluation can be done in real time for the circuit. I just want to give you an example to show you why smoothing is important. So here you see that is my example from before, and you see that it's not smooth. I can start to do the evaluation. So here I want to count the number of valuation, and here you see that. If you count and you reason, here I have that. So I can count here. I have one particular valuation, but I can take omega or not omega independently and to add to that, and you will do. So I have two valuations here. And the same way I have y that is not appearing. So if I reason about that, I have this one plus I can add, I can put y to 1 or 0 independently. So I have two. And then I can add both because there's a determinism, and I can add 4. And I will do how to show you how we do that in a bottom-up inductive manner. So you map the literal to 1 because here is this that we do. And then what I do, I associate the end to multiplication and to the or to the plus of the summing, and you do the propagation. Typically, with the multiplication, I multiply, it gives me 1 here, 1 here. The next step, I will multiply here, which is 1 here and 1 here. It's nothing difficult, but here you see that because it's not smooth in some way, if I just add things, I will only have 2 mappings, which is wrong. So what I have to do, I have to count the fact that here I had the W and not the Y, and here I have the Y and not the W. So the smoothing gives me the fact that I have to take it. Smoothing here we do that online, the smoothing, but in general, what you want to do is smooth one for all, and then after that. Question?
So smoothing can be done without any overhead.
Yeah, it can be offline. Here, I just wanted an example to see why is it important to do that.
But offline also, but it doesn't increase the size of the circuit.
You will is a part of the next slide, how costs the smoothing. And so typically, we do the smoothing, and then we add and we default. And the thing is, you take any summering and it works. That's the good thing. Commutative summary. The thing also what we've done is about enumeration, because this was we wanted to reprove that. So when we understood that, we say, okay, we can do probabilistic, and we ask, okay, can we do other things that works on trees very well? Typically, at the time, it was enumeration when we started the work. We ask, it was already proved by 2 different approaches, and we say, okay, can this approach can do this? So what we do is we tell that, okay, for trees. So when we look for trees, and we went to the DNF, and we had to work a little on it, and typically we have to have these 0 suppressed semantic DNF circuits, and what we know is the fact that we can enumerate it, satisfying the assignment with a preprocessing linear on C, and the linear in the size of the assignment. And I will show you after that the fact that it's not on the valuation but the assignment is really important if you want to use it for MS. And so typically we have to deal with different problems dealing with part of the circuit with the empty partial assignment, some memory usage that can, you have to be careful. In the general case, you can have a linear memory usage and things like that. And in practice, what we want to do is, I don't only enumerate the assignment, but I enumerate something a little bigger, which is I enumerate the variable gates and the AND gates of the acceptance subtree of the partial assignment. Typically, I take a node, I look at all the partial assignments, and what I do is when you do the proof for showing this partial assignment is true, you see with the AND you can combine things, but in the OR you just choose only one branch. In some way, all these OR that become a unary node, you just merge them to one. And I just look at these trees. And typically you have to find good structure to do that, but you can do that. And one key thing that is the fact that we need a structure that is a persistent set structure where I can do this following operation in grand O of 1. I can add an element, I can give an aberrating element and deleting element. So if you do that, just any list, anything works. But the thing is important that you can do a union of these two structures that doesn't depend on their size. And so typically, Louis Jachet proposes a structure like that. You can have your own. What is really important is that.
So is a new data structure created for this? It makes it.
Yeah, I mean, like here I just describe you in a more API way that what you need for proof, and we propose one particular kind of implementation for that, but you could have another one.
It's the practical one. This has been implemented. It's like
we have not implemented already. It's something that we would like to do at some point. The thing is important is also that the pre-processing, the way that we build things, are in a bottom-up evaluation in a linear way. And what we can do also is a lot of people have worked on rank enumeration recently for conjunctive queries and union of conjunctive queries. We had a great talk about that also before. And typically we ask ourselves what we can do with DDNNF. So what we have is that this zero suppressed semantic circuit, we use a strong subset monotone notion, a ranking function on the partial assignment, meaning that you only put weight on the positive part. You don't put weight on the negative part. I mean, you just count things that appear in the solution because they are assigned. And what we can prove that we can enumerate the following with the following order, following their cost in the pre-processing linear in the circuit, and a delay that depends on the maximal size of the assignment, and also k is the number of solutions that you already enumerated. So more you enumerate, more you have to pay. And in practice, we do the same thing. We rank enumerate the subtrees in the same way that we do for the enumerate case. And the main difference is the key structure that we use, and here we use Brodal queues. So what are these Brodal queues? They are really beautiful structure that they are persistent priority queues where I have the following property. I can add a pair element value in constant time. I can have the maximal in constant time. So this is a classical thing that you have with priority queue. The really important thing is the fact you can do the union of two sets also in constant time. And the classical thing with this priority queue is the fact that deletion is where you pay the cost. So this is the kind of result that we had in some way. We reproved in some way that things that were known in different contexts, and we proved that for this kind of circuits, a lot of things works well. With a little work with some really complex structure for this one, we are really, really happy that we found this structure because it's not a trivial one to do. And typically, this is what we have. The thing I wanted to remark is what causes the smoothing, because most of the time you need a smoothing, at least for reasoning with your solution. Smoothing is, in general, the bad news, is the fact that the size of the new circuit is in the MD square. Because you need to represent a lot of things, all the variables possibly, you have to look at all the combinations. The thing is, you have different, better case, if you have some particular kind of DDNNF, a structure one, Antoine worked on that and showed that you are close to a linear, but you're still a little above.
Yeah.
Right? And this was the result.
exactly you want to do.
Yeah. So if you want to have a linear preprocessing and you need to smooth this part, you need to pay a price that is a little more than linear, but not too much. You can ask Antoine about that. And also what we proved in a paper when we do enumeration is for other one is called ordered in NF. You can do that in a linear time, but you need a particular notion of gates that are we invented to have a compressed way to represent the value. So the question now is how we go back to M from to MS. So the question now is how I construct really the circuit representing the answer. So give me an automata with first order variables. There are ways to generalize that, but let's go. And when we want to, what I know I can build a smooth circuit capturing exactly the set of tuples in the output of A and T. This way, I can, if I do that, I do that in linear time in my tree, and then after that you reason on this, so still linear on your tree, your circuit, and if you want to compute something over tree motor, which is a summering, you can do it just by reducing that. What is important here is the fact that the smoothing is already done during the construction, so you don't have to redo that. And the second thing is the fact that for also tree automata, you can also build a tree in the zero suppressed mounting, capturing exactly the set of tuples on the output of the input. So here, what is important, this one is used for the enumeration. So here, in general, what you have to notice is the fact that the number of variables that you have are the number of variables of my automata multiplied by the variable by the node of my tree, which poses a problem because typically, if I look at valuation, a valuation is of size length of my tree, of the size of my tree. So if I just do reasoning over the valuation, I will not obtain the results that I want, that is linear, that the delay will be constant or the delay will be logarithmic, because typically I just have to put all the valuation that is already linear in the size of my tree. So it won't be able to do that. I won't be using just valuation, go back to the result. For that is why we use, so we are in the first order case, we know that the number of variables that are assigned to one is bounded by the number of variables in my query. I know that this part for an assignment, its size is only in size of the query, and therefore, if I look at only the data complexity, I'm just constant. So this is why we need this zero suppressed semantic to ensure in some way that we just enumerate the minimum number of information that we need for going back to the result. And I just want to show you a little how we build that. So typically, here I just want to take any pair of nodes of my tree. So it's a very simple thing. I do the Cartesian product of my tree, but I just want to show how you do that. You have the state where you know if you assign or if you have not assigned a variable, you assign alpha, you assign beta, and you assign alpha beta. And you have rules to the fact that, okay, if I assign beta on my left subtree, I find empty in my right subtree, and I don't assign anything on my current node, then the state of this node is beta. The same way I assign beta before on my left tree, the empty on my right tree, and now I set alpha to n, then I go to alpha beta. It's very simple, and this is a classical thing, just classical rules for tree automata. And now I will show you how to build the automata for that. So the circuit. So typically, we'll do that by induction, and I have a node particular variable that say alpha to n. This is the one I want to build, and also I assume that I have OR gates for different states of the previous nodes to the left, and the different states that are already computed. So this is the output of my output sub-circuits for when I go to the M state empty, 10 alpha, 10 beta, 10 alpha beta. And after that, I just apply the transition function in the classical way. Meaning that, okay, I use the first rule, okay, I'm beta, and I'm state beta and state empty. I do the end because then I have to compose that. And after that, if I don't select alpha n, I just go to beta. In the same way, now for the second rule, I define the data empty, but now I choose alpha, I put n to alpha, and then I can create alpha beta. And this intuitive manner, you just can do it, and it has all the good properties that we want. So this is super simple. So you're just expressing in natural ways the transition function that you have, all the runs that you have in your children. And therefore, we can reprove all the following complex queries that we have done. And what is important, I said, we notice that the size of the corresponding assignment is bounded by the search. This is very important because we cannot do that with evaluation. And the new result that we have is the fact that now if I do that for rank enumeration, I can do that with a preprocessing of T and a delay of log in case the number of answers produced so far. So kind of similar result that you have in conjunctive queries. But the main difference is the conjunctive queries. And I just want to talk 2 minutes about updates. The thing is also, the kind of structure and the kind of way we compute it is bottom-up, and works very well when we want to modify the tree, and what we want to maintain this circuit, and how much it costs. So when you do updates, you relabel, and in general, you don't want you want to maintain this data structure. And there are before results that look at that. And typically, the thing is, for text, we knew that there was something efficient, but typically for words, we had this complexity. Low square of T, low square of T. And the thing is, now, if we relabel, we know how to do that. We have a structure that we know that we have the delay that we have before for enumeration, and for the update, we need a log time. And so typically how it works, what we can see, we see that if I want to update my circuits that were built for Q and T, when I do an update of my tree, what I have to do is I have to do an update on C that I have to update C, and it depends only on the depth of C. And typically, then the problem now is the depth of T can be linear on T, and there are a lot of nice methods where you can rebalance your tree in a way to have the depth that is not the same. So there, if you just need rebalancing, you just need to balance at the beginning, and we don't need to do anything after that. And there are really nice things that say that I can do rebalancing with logarithmic time, and also results and very soon, very recent ones, such that you can maintain your percent of your tree in log square. And this recent one, which is under submission by some of my co-authors, I'm not there. I'm not in this paper. It's a very nice algebraic representation for trees, forest algebra. It's very nice work. And typically, they claim that it's and therefore, we have, in some way, this is where we can adapt. And because everything we have done before is a bottom-up evaluation, you see that you just have to propagate over the depth of the tree. And then after that, the depth of the circuit to maintain the structure. So just to finish, it was known that complex evaluation of MSO queries of our trees can be done efficiently. The thing is, we try to present a uniform framework to look at well-known results based on particular kind of circuits that are smooth or zero suppressed semantic DDNF. And for me, in some ways, the philosophy is why it works on trees is because you can have this representative solution for all the queries and not only for a fragment of them. And also, we show that because of our techniques, we can do incremental maintenance of the structure once we did all the results. And typically, there are a lot of things that have been done recently in relational databases for different kind of query and like uniform sampling, direct access, generalization of enumeration of weighted MSO, but for trees, and all these kind of things. And typically, we think that a good answer, a good approach for doing that is to look at this problem over this DNNF. Moreover, these DNNF are not used only in databases, but they are used in a lot of different framework for AI and for also different applications. And typically, when we find this result, is not an impact for MSO, but for more general context. Thank you.
questions? If not, we keep them. Yeah. Questions? Yes.
Sorry for such a silly question, but this Portlander algorithm for rebalancing, I assume this has a gigantic astronomical constant, right? As all Portlander algorithms have, right?
No, but yeah. The thing is, they are here we are very theoretical. The thing doesn't work in
This
practice.
is not a criticism of you. I just wanted to make sure that it's the usual kind of fixed payment practicability thing.
Yeah.
Just
Yeah, for the typically for it's a good question because I'm not sure. Linear on the time, yes, there is something, but it's still like this balancing doesn't depend on the query. So here you just have something about the tree, and I don't know the constant to do it, so I cannot tell. But yeah, it's not easy algorithm to do that in a really linear time.
or double exponential, like the stuff that he does with 3D computation.
In what would it be exponential?
In the tree width of some underlying combinatorial structure that shows up somewhere.
But we're doing this on a tree, so I think the tree width would be some constant, right? So it would be exponential.
Right,
constant.
It's of the query, right?
No, because I said this is only depend on the tree, doesn't depend on the query.
Okay. Then I don't understand, but it's not important actually, So,
No, the thing that you have to pay is the fact that MS a query, here we assume that we can translate it to deterministic tree automata, and this is the question of how you express the query. So there is a big constant for in how you express it. But most of the things I think they just depend on the query. But this thing I don't know. We have not implemented yet.
Okay, let's thank again. Yeah. I think for a general question, it's probably